Wow, 2 weeks we've gotten through how motion works, how that predicts where we're going to be. We have kinematic equations to help figure out which equations should be governing things. Earlier this week we talked about how forces cause that motion, and if you're applying a force on something that gives an acceleration, that acceleration can then be used in the kinematic equations. Yesterday we talked about collisions and how collisions can be used then to understand after things collide what happens to another. And if you're in an investigation like in a police accident reporter, that's their bread and butter. They spend the day talking about what's the coefficients of frictions, what are those motions end up being when two things collide, where do you expect the other bodies to be. And so that's a big career in that area. My niece's husband does this and trains police officers around the world. But I want to finish, though, with this idea that was collisions. Collisions are going to need momentum to solve. But we can now take that step if we have velocity, which is a measure of how fast things are going, to then individual collisions, which is mass times velocity. I want to get to an idea called energy, and that energy is, in a lot of ways, shows up all sorts of places. It also simplifies a lot of the work we're going to have to do. Now, energy is just the ability to do work. Okay? Energy is the ability to do work. That work may be in moving things around, causing things to get started. Pushing on a car gets it moving. That motion of that car is energy. It might be changing the potential to do more work. It's lifting some rocks up so that then when you go away, you can hit a lever and those rocks coming down will do work for you. That's potential energy. That's moving something higher in energy. It may be to move objects in a spring, to load a spring. That's energy you're putting in from your work to cause a spring to be attached so that when you pull the trigger, the spring expands and does work for you. But all of those are different ways to show energy. The first one I want to just talk about in terms of the work that gets done. It's like, hey, I got to move my house, I'm going to move a fridge, and I need to apply those. How do we calculate that work that's done? Now, work in scientific descriptions is the amount of force that causes a distance, some substance to move a distance. Now, I could push on this wall all day long, and I could sweat, and I could burn a lot of calories. But this wall is not going to move. So that distance is still going to be zero. Have I done any work? No. So the way science describes work is how much effect your force has had on moving an object. Now, you may also notice that there's an angle in there. And that's because it's the force that's in the direction of motion. So it's the component in the same direction as motion. Most of the time we're moving stuff along the floor, and it's the x part of your force. So you want the x part of the force that causes that, and that's the cosine theta times force times your distance. So let's do a calculation real quick about energy. And I'll put in a little angle in there first, okay, so that we can see what those look like. But if I take an object, like you take a wagon, okay, and I provide a 100 Newton force, and this wagon weighs, let's say, 100 kilograms. That's a pretty heavy wagon. Okay, and if I apply that 100 Newton force and we go down the road 50 meters. Okay, I've given you too much information because all I need for work is equal to the force that causes some change in distance. But the trouble is that force is not in this direction of that motion. What I need is this portion of that force, which is the x portion of that force. Okay? How do I get the x portion of any vector? The portion of the vector in the x is equal to the force times the cosine of theta. That's where that came from. The shadow of this. So we take the angle here, and let's make that 45 degrees. Okay? And then let's figure this out. I have 100 Newton force times the cosine of 45 times the 50 meters it took to move this. So scientifically, if I calculate that, I'm going to take 100 times the 45 cosine times the 50 meters. What I'm going to get is equal to 3,535 something. Well, let's look what you have. Newtons meters. Newtons times meters. And this is actually the unit for energy called a joule. A joule is how much energy gets used up. So that's moving a large mass, and you're applying a force in a long direction. 100 newtons is an okay, sized force. And 50 meters is half a football field, so 3,000 joules. How do those joules relate to your diet joules as energy? Well, joules are actually, in the diet you eat, are kilojoules, and it's 4,000 of them per calorie. So it's a small portion compared to what you would normally eat, and if you've ever gone to work out, it takes a long time to work your calorie joules down. But 3,500 joules, or if I wanted to put that prefix in there so that I could use this, it would be the same as kilojoules, right? And if you remember our little box method from joules, let's make that a little bigger. 3 boxes over is kilojoules. So I move the decimal 3 places, and this would become 3.535 kilojoules. Remember, 1 box, 2 box, 3 boxes over, and to the left. So that's the amount of work that ends up being done. That's the scientific description of work. Okay? So that's one of the problems that we would have to be able to figure out work, and that's just force times distance. A lot of times it's going to say, hey, if I hit a brake, how much work will that do for my bike? Okay, they know what the force is of your brake. Most of the time, those are going to all be aligned, and you won't even have to do the cosine part. Okay, let's take a look again at one of these others. Well, let's get you to take a look at the problems that are in the book, or that are posted alongside here, so you can work on those.